Hello, everyone. Sorry about that. Nice to see you all again. Let's go ahead. Okay, great. Everyone can hear me, right? We're good? Okay, so we're going to talk about some things today which are moving in away from the previous topic. We're done with inclusion, exclusion. And now let's talk a little bit about binomial coefficients. For that, I actually want to start with a famous class of questions, which is important to talk about, just to make sure everyone has these tools. Now, this is something which I understand that in some classes and concepts, you guys already talked about this. But just to make sure everyone's on the same page, I want to make sure that we talk about this too. And so this one I often call something like pirates and gold. It's like if you have n pirates, and if you have k gold coins, and those k gold coins are indistinguishable, the classic question is, how many ways are there to distribute these coins among the pirates? How many ways to distribute coins to pirates? Now, with these kinds of questions, there's usually two variants. I mean, one kind of it is where you say that we have no constraint on how many coins anyone gets. One version is where it's okay to have 0 coins. And the other one is where everyone needs at least 1. But this one is the first version. It's okay to give 0 coins to a pirate. Now, with these kinds of questions, it's also important to emphasize that you can't give half a coin. Otherwise, the answer would be infinitely many ways, because you could just cut the coins up in all kinds of funny ways. But it's just that some non-negative integer. So again, this kind of question is well known. And let's just bring everybody onto the same page to make sure that we all have this tool. Anyone have a sense of how you approach these kinds of questions? Okay. Venkatesh. Okay, just a second. Pirates, x1, x2 up to xn.
Yeah, and that's like the amount of coins that they get.
Tell how many coins. Yep.
And then is equal to k. So now basically you just have to solve. You want to find the number of solutions for which that quantity is equal to k.
Yep. And you're counting the number of solutions to this, and you're saying that's like a classic problem that you've learned before. Is that the idea? How to solve. Okay. And there was another thing some people have said, stars and bars. Sometimes it's called stars and bars. Sometimes it's called sticks and stones. Effectively, the way you think of this, again, since this is often taught in other classes, the way that I often think of it is I actually use the original version, the pirates and the gold. I find that actually easier than the x1 to xn. And if I'm using the original version, then what I'm talking about is I can actually think of drawing a diagram, right? I can say, for example, if I draw something like this, some things here, I'm going to put 2 of these vertical bars there. I'm just drawing something, okay? And what I've just drawn is a situation where I have 6 gold coins and 4 pirates. So this corresponds to 6 coins and 4 pirates. And it's a very particular distribution. The way that these coins got distributed is that the first pirate got 3, the second pirate got 0, the third pirate got 2, and the last pirate got 1. Is that clear? Like the way you can read this diagram is you just read it as if those vertical bars are the separators between the different kinds of pirates. Between the different pirates themselves, and then these dots, these are just the dots, which are how many coins there are in each batch. So if I did something like this, every one of these diagrams corresponds to a different way to separate 6 coins among 4 pirates. For example, I could also do this. I could put all 6 of the coins in front, and then I could put all 3 of the barriers, and that means that the first pirate got 6, then the second pirate got 0, third got 0, and the fourth got 0. And it's also important to note that another way to do this would be all the bars first, and then the 6 coins. And that would be saying that the first pirate got 0, second got 0, third got 0, and the fourth got 6. But I'm emphasizing that each of these last 2 counts differently. And the reason is because the pirates have feelings and the coins don't. So somehow, like, that's just how it is. Coins are coins, right? And so this first pirate got 6, and then later the first pirate got 0. So that's a different distribution. Does this make sense? I'm basically saying that every rearrangement of this kind of a drawing gives you exactly one of the ways to distribute these coins among these pirates. Okay, and this is a classic hard problem because if you don't think of drawing these kinds of diagrams, it's actually really hard to do. We'll see another way to come up with the formula soon, though. After we get one formula for this, I want to do another way to get the same problem. So in that case, let's finish this up. Suppose I have like n coins and n pirates and k gold coins. Can someone help me translate this interpretation into some kind of a formula? You can tell me the formula in terms of a choose, or you can use factorials. Either is okay. And you can just type RH or raise hand if you want to say it instead of typing it. Andres.
Could it be something like n plus k minus 1, choose n minus 1?
Okay, so the way that came about is you said, how many of each kind of thing are there? Well, what I see here is that in all of these, the number of these solid things, the number of dots, is the number of coins. So k of these, and then there are n minus 1. Oh no. Let me use some colors, because otherwise it looks like those are ones. So n these, and n minus 1 of these golden bars. Does this make sense? I'm just emphasizing I'm using the colors just to split the 2 different kinds. So it's not like it's n minus 1 ones. And that's how many of these things I have, and I'm just trying to rearrange them. And we've seen that. If we're ever trying to rearrange a bunch of symbols, where I have like a bunch of R's and a bunch of L's, we saw this thing, the answer is like, take all of the symbols that you've got, all the positions that you've got, and choose where you put, I don't know, your favorite one. You said, did you say choose n minus 1 or choose k? Which one did you say?
I said choose n minus 1.
Choose n minus 1, okay. So the number of rearrangements is equal to, it's all together how many of these things are there, k plus n minus 1 slots for putting things, choosing n minus 1 of where I put those vertical bars. But by the way, I asked you that question because there's 2 answers to this. Well, there's lots of answers, but there's another way to write the same thing, because it could also be k plus n minus 1, choose k. Because you could also decide, where am I putting those golden coins, right? I have to put k of them down. So this is the formula that comes out of this kind of a problem. If you haven't seen this idea before, these are famous hard problems. But now I want to go and do it a different way. The other way comes from saying, let's just try to do a small version of this. Let's do some small versions of this problem, and we'll notice some really, really nifty patterns. Okay? So the first one is, if I wanted to ask a question with just like 2 pirates. Suppose I have 8 coins and 2 pirates. How many ways? And here, the number of ways I'm allowing a pirate to get 0. And I'm also saying for this one, you don't need to use a really fancy formula. Can anyone tell me how you do this? Braden.
Well, you say that you'll give some value of points from 0 to 8 the first pirate, and then the second pirate gets the rest.
Yes.
So you have 9 choices for the first pirate, and you just have 9 choices.
9, since the first pirate gets 0 up to 8, and then the second pirate gets the rest. Okay, so what I've just found out is if I have 8 coins, 2 pirates, then the answer is going to be 8 plus 1, which is 9. That's kind of nice. What if I have 3 pirates? Suppose I had 8 coins, 3 pirates. Number of ways equals. Now, what I want to do here is there was someone who came to office hours today who had an idea on how to do these kinds of questions, where the person said, you know, what if we just kind of branch off based on what happens to the first pirate? You could do that, right? The first pirate, that's what we did before. The first pirate's going to get anywhere from 0 to 9. Okay, so it's like the first pirate gets 0. First pirate could get 0 or 1 or all the way, not up to 9, all the way up to 8. Is that okay? So these are all, I'm going to draw a giant tree diagram. So if the first one gets 0 up to 8, now this person had a clever idea. They said, in that case, if I've already given to the first, what's left over? Here, the second and third, they have to split 8. Does that make sense? Because if you gave 0 to the first one, the second and third, they split 8. How many ways are there for the second and third pirate to split 8? Well, we've sort of seen that already, right? We just did that. We know that if you have 2 pirates splitting some number of coins, the answer is just number of coins plus 1. Okay? So this is telling you the number of things, number of ways. Here is 9. But how about the second row? Well, if the first pirate gets 1, how much do the second and third have to split? 7. And then the number of ways would be 7 plus 1. Again, because of the way that the logic works for just 2 pirates, you can just give the first one anything from 0 to the total number, and that's like the total number plus 1 options. 8. And it will go all the way down to the last one, split 0. And here's where we can see that our conventions make sense. How many ways are there for 2 people to split nothing? There's actually 1 way, not 0 ways. The 1 way is like this. There's nothing. And that is actually 1 way. So what we found out now is that this big sum is from 9 down to 1. Or 1 plus 2 plus 3 up to 9. What's the formula for 1 plus 2 plus 3 up to 9? We've got a formula for that. We've already learned that by this point in the math for everyone that you guys have been doing. It's like, anyone want to do a raise hand on this? Okay, I see something. This is from Thomas. 9 times 10 over 2. 9 times 10 over 2. Hey, can I write that as a choose? That is a choose. 9 times 10 over 2 happens to be a choose. That happens to be, people are saying this is n plus 1 choose 2. I think this is 10 choose 2. So it looks like what we just found out is in general, it's going to be like, I think it's n plus 2 choose 2 is what we're going to get, right? If I have n, if I replace with the 8 becomes an n, it's like n coins 3 pirates ends up being n plus 2 choose 2, which is actually consistent with what we've proven before. So over here, if I had in general, if this was n coins, 3 pirates, that's going to give me n plus 2 choose 2 ways. Now, why am I doing this? I'm going to do it one more step. And the reason is because there was an old exam problem that somebody was looking at, and that's why the person came to the office hours. And the old exam question had like splitting among 4 pirates. Well, what else could happen? Suppose I have, now let's just use n, okay? Suppose I have n pirates. No, it's n coins. N coins 4 pirates. I've just flipped the n and the k, okay? But when in math, you can use a letter to represent whatever you want. N coins 4 pirates. Number of ways equals. Well, what you can do is you can still say the first pirate, how many are you going to get? From 0 to 1, all the way down to n, okay? But now we can recurse. This is actually what people wanted to do. Ooh, there's a comment. Can we also write the first one as n plus 1 choose 1? Yes, of course. There's a nice pattern. What happened here? Yeah, so the first one is n plus 1, and that is n plus 1 choose 1. Absolutely. So there's a pattern. N plus 1 choose 1 over there, n plus 2 choose 2 over there. Well, we probably are going to get n plus 3 choose 3, but why? That's what we want to figure out. So if I look at this like 0, 1 up to n, how do I continue? Can someone help me out here? I want to continue the logic I did previously, and I want to find something nifty. Brayden.
Once we've given some number of points to the first pirate, if we just look at the x or something, then the next pirates are going to be getting, or sharing n minus x coins among the three of them. Yeah, and we already know what the number of possibilities for that is going to be.
Okay. So I unfortunately was not so clever as to write an x. Oh, I still have space. Here's an x for you. So that's like sharing, share n minus x, okay? And the number of ways, we know how to do that. Oh yeah, it's sharing among, wait, what do you mean second to nth? I wrote it wrong. Second to fourth, second, third, and fourth. There's no nth pirate. Second, third, and fourth. Okay, so between those second, third, and fourth, that's 3 pirates, and we know the answer there. That's the number you're sharing plus 2, choose 2. So we have n plus 2, choose 2 ways. This is going to be n minus 1 plus 2 is n plus 1, choose 2. This is n minus x and then plus a 2, choose 2. And this is 0 plus 2, choose 2. Oh, how nice, that's 1. That's nice. I do expect it to be 1 at the end. Now, we actually already proved it another way, that somehow the sum of all of these things magically is supposed to be n plus 3 choose 3. We know that from this like sticks and stones argument. But what we just discovered is, that's neat. It looks like if you add up these things, the answer is always going to be n plus 3 choose 3. By the way, we already have a proof of that. That proof is called the other thing we did. The other thing we did, this is called counting in 2 ways. We found one way to count how many ways can you distribute n coins among 4 pirates. And we know from the previous thing, it's n plus 3 choose 3. Therefore, I now have a proof that this whole sum is equal to n plus 3 choose 3. Okay? That's neat. But in math, we're all about finding lots of different ways to prove the same thing. And turns out that we're onto something. Advait, what did you want to say?
I was going to say, I'm pretty sure there are like a ton of identities that look just like this, and they're all like collectively given the name the hockey stick identity.
Hockey. Hockey stick. What hockey stick? I don't see any hockey, although it is pretty cold in some parts of the country. So if you want to say hockey stick, I need to draw Pascal's triangle. I think that's what you're getting at. Let's go and draw Pascal's triangle. And where are all these like choose 2 things? Well, I'm going to use some color coding. Okay? In Pascal's triangle, here's what it looks like. I have a 0 choose 0. That's the top. I have a 1 choose 0. I have a 1 choose 1. I have a 2 choose 0, a 2 choose 1. And now the 2 choose 2, I'm going to use yellow, just because that's what I've used over there. This is 2 choose 2. Next, let's go to the 3 row. 3 choose 0, 3 choose 1. 3 choose 2 is yellow. And then there's this 3 choose 3. Okay, and then there's 4 choose 0, 4 choose 1. I'm going to be lazy, so I'm going to stop this row. I'm not going to write the 5th row. Well, actually, I will for a different reason. 4 choose 3, and 4 choose 4. But I won't write the 5th row, the row for the 5 chooses quite yet. So I've written all of this, and I've gotten like this sum, these things. But magically, I mean, we somehow know that if I add these stuff choose 2, 2 choose 2, 3 choose 2, 4 choose 2, all the way up until n plus 2 choose 2, somehow the answer is supposed to be n plus 3 choose 3. So the sum, what's a good color for this? The sum of all of these things, where is that supposed to be in Pascal's triangle? I've drawn Pascal's triangle, the sum of this particular diagonal is supposed to be a very specific number, a specific position inside this triangle. Where is it? I've got 2 choose 2, 3 choose 2, 4 choose 2. It's supposed to add up to what choose 3? Braden. Yeah, that's right here. 5 choose 3 is here. That's why this is called a hockey stick identity, because it looks like a hockey stick. If you go down a stripe, a diagonal stripe in Pascal's triangle, where your slope of your diagonal is the same as the slope of the left edge, if you just add, your answer is always the thing down there. This is called the hockey stick identity, or theorem, or whatever. Let's go and prove this thing. Okay, let's go and prove this. By the way, we could have said, well, we already proved something with this counting in 2 ways, but there's a more direct way to prove the hockey stick identity of why if I just go and add up all of these, then I'll get that next one. Oh, question. And the other way, yes, Advait, you're right. Because Pascal's triangle is symmetric. If I went the other way and took the other kind of diagonal, then the sum would be, the hockey stick, but pointing the other way. Okay, so that you can put the hockey stick in either way. Okay, so now, yes, exactly, Sean, thanks, by symmetry. So now let's go about proving this this particular hockey stick identity. To get to that, the easiest way to do it is to actually first say, I didn't really give you I did give you a proof of why in Pascal's triangle, when I add 2 of these chooses, then I get the choose which is right under them. I told you that was because we could think of all these like paths through a diagonal grid. That was a legitimate proof. But there's another very simple proof of that, where you don't even need to think about paths. You can think of these as counting the number of ways to pick a subset of a particular size from a bunch of stuff. Okay? So let's start talking about all of these binomial Pascal's triangle identities. The first is one which is the simplest fact, which is that if I take n choose k plus n choose k plus 1, what is that? Well, think about where they are in Pascal's triangle. N choose k plus 1, we want them to add to the thing right underneath it, right? And the thing right underneath it is going to be n plus 1 choose something, because that's the next row down. And every time I do these things, I always have to ask myself, n plus 1 choose what? Is it choose k, or is it choose k plus 1, or is it k plus 2, or k minus 1? And the way I always think of it is, look, when I take Pascal's triangle, if I go 1 row down, it kind of goes across diagonally this way. Do you know what I mean? Like if that was choose k's would be there. It's like the choose zeros are here and then just going along on that edge. And then the choose 1s are going this way. So the thing that they should add up to is choose k plus 1. Okay, let's prove this. It turns out that we can prove this just by even another counting in 2 ways, which is even easier, which is just like, what does it mean anyway? It means the number of ways to pick a subset of k plus 1 things from n plus 1 things. So I'll call it the right-hand side is equal to the number of ways to pick k plus 1 things from n plus 1 total things. Okay, that's legit. Now, if I'm supposed to pick k plus 1 things, I can break into 2 cases. And whenever you break into cases, you just make sure they are mutually exclusive and they cover everything. We've got 2 types. Let's just draw it this way, actually. 2 types. One type is where you pick the n plus first thing. And the other type is where you don't. And it's pretty clear that if you're going to pick k plus 1 things, you're either going to pick the n plus first thing or you're not. Okay, so that's very clear that this has split into two disjoint things, and between them you've covered every possibility. Well, how many ways can I do this? Suppose I've picked the n plus first thing. How many ways can I pick k plus 1 total things from n things if I've actually already picked the n plus first thing? How do I think about this one? Andrew.
I was just saying it's actually just the left-hand side.
Left-hand side.
You're just reserving one, so you just when you reserve one, then you choose k, and if you don't reserve that one, then you choose k plus 1, and you just sum them together.
Yep. Pick k from the first n things. And that's equal to just n choose k. And the other one is where you don't, so you better pick k plus 1 from the first n things. Pick k plus 1 from the first n, which is equal to n choose k plus 1. Okay, so this is very basic identity, which is the heart of how you make Pascal's triangle at all. It's you take these two things, you add them together, you get the thing underneath it. That's easy to prove with this way of counting the number of ways to get a subset. Now I want to use that to get this hockey stick identity. How could I do that? Well, now I'm going to make a Pascal's triangle. That's Pascal's triangle. And suppose I'm going to do a sum which is going along here. It doesn't even need to be the choose 2's sum. I'm just taking the sum going down. My goal is to show that the sum adds up there. Okay? What might be a good way to do this? Well, let's go and try to use induction. If I wanted to use induction to prove this picture, what would a base case look like? There are actually lots of different base cases that I have to worry about, because I could be talking about going down this particular diagonal, or I could be going down this other parallel diagonal. Can someone help me out and give me a simple base case? Eric. So what I heard you say is n choose n. So what you're saying is a base case to prove this would be, boop, just that one. And those are all 1 anyway. So the sum of that, which is just 1, is this, which is also 1. Is that clear? For the base case of proving this kind of a thing, the base case, there's that infinite family of base cases. Those are just where I grab the thing on the very edge, I say that's my diagonal, I'm stopping there. And the sum is just this one down here, because they're all 1s anyway. Is that clear to people? That's the base cases. There's all these base cases. So what I'll write is, maybe I'll write over here, these are all the base cases. Okay, so if those are all the base cases, now I need to know what does the induction step look like. Induction step means I have something like this. In fact, this is going to be my picture for this kind of induction step. It's suppose I already know that the sum of all of this happens to be there. For the induction step, which I'm going to label on the left picture now, induction step, what I've gotten is I know that the sum of all of this is equal to that. But I'm greedy. I want to do more. I also want one more. How do I know that the sum of all of this is there? Jack.
Well, so ideally, we know that we're going to go to the next row, and there's a number in that blue spot, and we can add it to the number in the green spot that we got from our induction hypothesis, and then check if it actually works. I hope it does.
Yeah, great. So what you're saying is okay, look, I know that the sum of this part is there. Okay, so I'm going to call it the sum of the induction hypothesis. Yeah, induction hypothesis. That's what it's called. This is the sum from induction hypothesis. All right. But now what I'm trying to do for my induction step is I get one more thing. All right. So now I need to know, why is it that if I take all of the green highlighted thing plus the blue spot, why does it land there? And Pascal's identity, the thing we just saw. It's because, look, the new thing is that blue spot. I already know that all that green stuff added to that. So I already know by that Pascal triangle identity that the sum of these two is there. That's why it works. Like, that's the entire proof of the hockey stick. Okay? So now what I know is this thing here is the new one. Maybe let me use white to stand out more. This is the new one, right? And so if I have the new one plus the sum of all the old ones, well, that's here. That's the new sum of everything. So this thing, I'll draw two arrows. This is the new sum of everything. Bang, you're done. So that means that the sum of this new thing, this induction step, is exactly what you expected it to be. And you can just crawl your way through Pascal's triangle that way. It's actually that Pascal's identity, that's what I call it. But the Pascal identity of like adding two things above gives you the thing below, that's like the tool you get to use for these induction type proofs. Okay, so that's actually why this hockey stick identity is true. Hockey stick theorem is true. I'm going to give another proof of it too. If you can tell, today we're basically talking about all these like nifty things about Pascal's triangle and different ways that you can prove things, which we have already related to this pirates and gold thing. Oh yeah, and now we know why that pirates and gold thing works. If I pull back, it's like, well, that's just the hockey stick identity. Add up all of these things, that's n plus 3 choose 3. That's why this works. So this is sum n plus 3 choose 3. And then the person who came to me in office hours and said, you know, what if I try to do this splitting thing? What I told the person is, it's a little bit complicated. It can be done. And this is how you do it. You could actually conceivably do this with 5 pirates also. Do you see what would end up happening? If you did it with 5 pirates, then I get all this stuff and it's all choose 3. Which by the hockey stick identity gives me the thing choose 4. So you can actually use this way of thinking to go and prove the whole sticks and stones, stars and bars, dividing pirates into gold and... No, dividing gold into pirates. Anyway, these kinds of things, they all actually are interconnected in that way. I'm going to pause here and ask, does everything here make sense so far? Because we just intertwined 2 key parts, which is this Pascal triangle as well as this pirates and gold. I want to give you one more thing about the pirates and gold before we continue to fly off into Pascal's triangle, and it's that twist. Remember I said at the beginning that we said it's okay to give 0 coins to a pirate. Well, what if the pirates don't want to be paid nothing? So suppose we put some rule. Suppose everyone needs at least 1 coin. That's like the standard variant of this, because these things like x1 plus x2 up to xn equals k, one version of this is where they're all non-negative integers. The other version of this is where they're all positive integers. Let's just deal with that right now. Let's just throw some actual numbers so that I can do it easier. Suppose I have 7 coins and I have 4 pirates. How many ways to distribute to give where every pirate gets at least 1? Oh no, everything broke. We need to go back to the drawing board? Well, not really. Sean.
You can give every pirate 1 gold, and then you have the old problem again.
Yes. We love this. We love to reduce problems to old problems. First, give every pirate 1. 1 gold. Okay? Then we have the old problem. Because it's like, great, you're happy now, you got your pay, let's go back to the old thing where we're allowed to give you nothing more. So if you do this, then what you have is you have 3 coins left. 4 pirates. And now it's the old problem. The number of additional coins you get is just a bigger equals 0. And so what's the answer to this? It's like, I'm always slow with this. I always actually just draw out what I'm dealing with. 3 coins, 3 separators for the pirates, because I'm very bad at forgetting which one's supposed to be -1 or whatever. But this is the general picture. 3 gold coins to split among 3 vertical bars, because I only need 3 vertical bars to separate 4 things. And so that looks like a 6 choose 3. And some people sometimes write this in terms of the n and the k, and there's some formula. It's like got an n minus k or whatever. I don't actually usually think about things that way. Oh, I guess I could. It's like n minus 1 choose k minus 1 or something. Maybe. But I always just draw it, and then I figure it out. Okay, so that finishes this whole pirates and gold thing. This is the classic hard problem in the early stage of combinatorics, counting things, where you wouldn't think of doing like these like dots and bars. But now we also see that if you understand Pascal's triangle, even if you didn't know this, you could force it out by expecting that Pascal's triangle is full of surprises. Along those lines, I want to give you another surprise, which is in Pascal's triangle. And this particular statement is one which has a complicated name. I remember the first time I saw this statement's name, I said it must be a very hard statement because it's so long. It's called Vandermonde Vandermonde's convolution. Okay, Vandermonde's convolution. And what this statement says is I'll give it with some numbers. Well, maybe not numbers. I'll use letters. So if I have I will use numbers. If I have something like 7 choose 0 times, let's choose some other number, like 10. No, 10 has 2 digits. It's too long. 9 choose 5. Okay. What I'm going to do is I'm going to keep 7 choose stuff and keep 9 choose stuff, but I'm going to let those things on the bottom move. Oh, let's use some colors. That'll be better. So let's go and use 0 and 5, then 1 and 4, and then 7 choose something times 9 choose something, but those will be 2 and 3, plus 7 choose something, 9 choose something, and then it becomes 3 and 2, plus 7 choose something, 9 choose something. You can hopefully see the pattern of what's going on. And this will be 4 and 1. And the last one is going to be 7 choose something, 9 choose something. And those will be 5 and 0. This turns out to equal something nice. First, before we say what it equals, I mean, most of the time you'll see this with like big sigma notations, like summation notations, and n's and k's and i's. I like to just do this because you can see the pattern. Can anyone tell me what pattern you observe me doing, just so that we're all saying that we're looking at the same thing? What's going on? How did I choose to write this stuff down? It's saying. Okay, good. So the bottom stuff, it always adds up to 5. And I found all the different ways to add up to 5 on the bottom. Okay? And on the top, I stuck something on 7 and I stuck the other thing on 9. And Vandermonde's convolution says, well, if you stick the first one at 7 and the second one at 9, and it works with other numbers, not just 7 and 9, and you kind of let the bottom thing move over all the different ways to add up to 5, what are we actually counting? Well, here, let's write the proof without telling you what we're proving. But as we write it down, it'll be clear what we're counting. I'm going to think of this as a lump of 7 things. Let's use squares, okay, or rectangles. So here's a lump of 7 things. 1, 2, 3, 4, 5, 6, 7. So there's 7 things in there. I'll just draw once the 7 just to indicate there's 7 things there. And then I have a lump of 9 things. Should be a bit longer. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 things. The first part is telling me I'm going to find out how many ways I pick nothing from here and pick 5 things from there. So the first part is pick 0 from here, multiply by pick 5 things from there. Okay? Then we're going to add to the number of ways where I picked 1 thing from the first one, multiplied by picking 4 things from the second one, adding all the way down until I pick 5 things from the first one and I pick 0 things from the last one. What's going on here? Is there a more nice way or more compact way to explain what's going on? Can you see that we're doing some picking? Thomas?
You're just like partitioning the different ways to pick 5 from either, so you can just use stars and bars for 7 plus 9 and 5.
Okay, so I think I don't want to use the stars and bars thing because I don't see how to use that immediately, but I want to use the rest of what you said, which is I'm picking 5 things. From how much? From 7 plus 9 things. So the answer is just 7 plus 9, choose 5. Right? Because if I add all of this together, it's just pick 5 things from anywhere. Pick 5 things from the 7 plus 9. Did that make sense to people? It's like, look, if you just look at it, I got 7 things here, I got 9 things there. How do you pick 5 things? Well, but you can think of the 5 things as being split across how many in the first batch, how many in the second batch. And that is, by the way, why, as Isain observed, these things that I'm choosing, they always add up to 5, and they're kind of moving in opposite directions, because I'm just trying to say, how many are you picking from the first batch, and how many from the second? So that's just this Manns convolution. It's a really fancy word, but it just talks about I have a big set, which is 7 plus 9, 16. And from that set, I'm picking some stuff. And it happens to be the case that if I decide how I split the set, then I could go and I can say that adding up all of these different possibilities gives me that last one. Okay, question. Andrew. Does that hold for a higher number of chooses? Yeah, it does. I mean, you see, the beautiful thing about all of this combinatorial arguments is I don't want you to memorize a particular argument. It's more of like trying to open the mind that there are lots of these different ways that you can count things. Okay? And what we have just seen is we've seen different ways of proving these identities. One of them was where I went back and I said, look, you could count something and break it into 2 possibilities, whether the last one was in or whether the last one is out. Or over here, we can do something where I've got the 7 plus 9 stuff and I kind of arbitrarily cut it into 2 pieces, and you see how your set of 5 things overlaps with those. And then over here, we actually used induction to go and prove one of these binomial coefficient identities. That's what they're called. But I used induction to prove. And maybe to finish up for today, I want to say this last one that we just used induction to prove, you can also write that as a story of counting things in 2 ways without using any induction at all. Let's go back to the hockey stick. The goal, of course, is if you've seen all these different ways, then hopefully if you're thinking about something, you can also creatively come up with your own way to count something in 2 ways. So, alternative proof of the hockey stick. Well, what was the theorem? The theorem was, let's write it now. The theorem is, I could think of it as k choose k plus k plus 1 choose k plus k plus 2 choose k. Remember it was choose 2 before, but it's true of anything. Plus up to n choose k. The answer was supposed to be the n plus 1 choose the k plus 1. What is this? I'm not taking that. Okay, so this is supposed to add up like this. And now here's another way to prove it. Now let's think of counting things. So what are we counting? N plus 1 choose k plus 1. That's the number of ways to pick k plus 1 things from n plus 1 things. Okay? So on the one hand, let's call it the RHS. The right-hand side is equal to the number of ways to pick k plus 1 things And now I'm going to name the n plus 1 things. From 1, 2, 3, all the way up until n plus 1. All right, they all have names now, 1, 2, 3, up to n plus 1. Now, here's a way you could split this. Oh, Advait, do you have the idea?
I think I have an idea.
What's your idea?
What if you case on the biggest number in your subset?
Yes, that's why I wanted to give these names, okay? So whenever you use the word case on, whenever I want to spread all this apart into all of these mutually exclusive, disjoint but covering all cases, I need to think about something that I could iterate over. And there is going to be a biggest thing that I've picked, because all these numbers, they're called 1, 2, up to n plus 1. One of them is the biggest. So what you can do is you can say this is equal to the number of ways where the biggest is equal to n plus 1. Oh no, there's a equals and an equals, so let's put parentheses, okay? English language should have been invented with the ability to put arbitrary nesting of parentheses. Actually, that would be terrible. Then you'd have to, in your text editor, you need the match parens command all the time. Never mind. Okay, and plus the number of ways where the biggest is equal to n, plus the number of ways where the biggest is equal to n minus 1, plus ... plus the number of ways where your biggest is equal to 1. We're going to get some of these to be 0, by the way, because, for example, if k was 50, there's no ways to make the biggest equal to 1. But we'll see how to deal with that soon. Now, let's do them one at a time. Suppose I want to know how many ways can I pick k plus 1 things from n plus 1, from 1, 2, 3 up to n plus 1, where the biggest one is that one. Can anyone tell me how many ways I could do this? And why? Braden.
Well, at this point, you've already chosen n plus 1, and so we need to take n, or we need to take k of the remaining n elements to pass to n plus 1.
Yep. 1 up until n, which is just equal to n choose k. All right, and that was the last thing I've got there. Remember, if I've cased on the largest thing, now it's done. I got it. I need to pick k plus 1 things. That's one of them. And the rest all have to be picked from the stuff before it. And if you see where this is going, the second one is going to be pick k things, but now from 1 up until n minus 1. Hooray! That's n minus 1 choose k. Because I have n minus 1 stuff from which I pick k. So if you see what's going to happen, I add it all the way down. The next one's going to be n minus 1 choose k minus 1. No, it's not. It's going to be n minus 2 choose k. And it goes all the way down to 0 choose k. So apparently what I've proven is something more. I've proven that if I take 0 choose k plus 1 choose k all the way up to n choose k, then it's the right-hand side. How do I reconcile this and finish? I'm supposed to do from k choose k. What's up with the 0 choose k? Sydney.
You can never have your largest element be less than k, otherwise it just doesn't work.
Yeah, so the important, okay, that's one way to put it. It's like, oh, come on, you're picking k things. Stop there, right? Stop at the k. Because there's no more. The rest are all 0. That's one nice way to do it. If I do that, I'm going to write this as, wait a second. No, last one, k plus 1, k plus 1. I'm picking k plus 1 things, okay? If I have a k plus 1 there, that goes to a k choose k. And then what the rest is the rest are all 0, since no way the largest is any of 1, 2, up until k. Yeah, because I'm picking k plus 1 things, so there's no way I can have that as the largest. Another way to say the same thing is that, like, 5 choose 200 is 0. There's no way to choose 200 things from 5 things. Both of those finish it. And so this is now giving you the proof of this identity, because I've added all these things, and I got the right-hand side. And that's the principle of counting things in 2 ways. And now we have just found out that this Pascal triangle is full of all these nifty coincidences that you can prove in all kinds of ways. That finishes the class.
Thank you.
Yeah.
Thank you.
Thank you.
Do it.